5/10 minus 2/10. So you get 3/2 times 3/10, which is 9/20. So that's the answer. Okay, questions on that? Yes? Okay. So the question was, why did we square it separately? And why not the whole quantity squared like this? Right? So, so one way to think about the here, let me come back to that. Let's do a simple example of like with just squares, and then I'll come back to that and we'll talk about why. Okay? Because that'll be it'll give me better tools to explain. Good question. Other questions that I can put off till later in the lesson? Yeah. Great. We'll talk about that when we do the derivations. Okay. Other questions? Oh yeah, a moon problem. Anyone have ideas about the moon problem? Yeah, go ahead. So maybe there's like a dynamic thing, so things get pulled over this way, and then when they kind of whiplash, they get pulled back. Okay.
Is it because the Earth's spinning, so the water's like goes outward, just keeps trapping the other way?
It's close to that. The moon is also so you like. Okay. Yeah. But why would that keep the water away? I know. Okay. So the closest explanation I know goes to this. It's a spinning problem, but it's not that the Earth is spinning. If the Earth was just spinning, like this wouldn't happen if the Earth was just spinning around its axis and the moon was stationary. If they were just like that, we wouldn't have another tide. But the moon and the Earth are rotating around a center of gravity of the system. And that center of gravity of the system is not. It's not on the axis of the Earth. So that center of gravity of the system is like right here or something. And so this water out here, just because of the centrifugal force, it's spinning around and it's far away from the axis, it feels the force and it's getting pulled away to the other side because of the centrifugal force of the system. So yeah, but because this water is closer to the axis, it doesn't feel much force from the spinning of the system, and the moon force is a lot harder. So now you know why we have two tides. It has to do with the center of gravity of that system, and if you know the mass of the Earth and the mass of the moon, you can figure out where that, and the distance they are apart, you can figure out where that is. Okay. All right. Yeah, so it would be high tide towards the moon and away from the moon, and low tide on this side. So this is low, and low tide on the other side too. So, okay. Let me do a quick demonstration here. I have a yardstick balanced on a pen, somewhat balanced on a pen, and I have some magnets here. So here I have 5 magnets, and I'm going to put them 6 inches away from the fulcrum. So 1, 2, 3, 4, 5, 6. Okay? And here I have 4 magnets. Where should I put the 4 magnets on the other side to make it balanced? So you guys can figure that out. I've got 6, how many did I say? 6? 5. I've got 5 magnets that are 6 inches away, and now I have 4 magnets here. Where do I put that to make it balanced on the other side, and why? Why would you say 7.5? Okay. So the weight times the distance from the fulcrum on one side has to be the same as the other side. So weight times the distance, and here the weight is 4, so I need 4 times something that equals 30. Right? The 5 times the 6 will be 30, so 4 times what? Is it 7.5? 2, 3, 4, 5, 6, 7.5-ish. That's a little bit. I think it's the 6. But you can see it's pretty close. Woohoo! Okay. I saw an old comic routine. Had these jugglers, and one of the things they did is they took a board and they put it on a pipe that was about this big around. And to make things more exciting, they called it the roly-poly of death. So this is as close as we get to the roly-poly of death in this class. All right. So a key here is understanding that things balance when you have a mass and the distance of 1 from the. This is the distance from the balancing point. Equals the mass times the distance from the balancing point of the other one. If those are equal, then they balance. But usually we don't know the balancing point. Usually we know the masses and coordinates, and we're trying to find the balancing point. So the way that we do that is you calculate what are called moments, the mass times the distance of all the parts of your system. And then you add those moments together and you divide by the total mass. Okay? Usually in ours, our mass is just area, the area associated with a point. So if you don't want to think about area, you can think about the area is just the area with some thickness, some constant thickness, like a plate or a piece of cardboard or a piece of wood or something like that. So this gives us the center of gravity of the system, x bar or y bar. So this is that gives us the balancing point for D. So do another simple example. So if this is 3 and this is 3 and this is 2 and this is 2, and we put the axis, we put the origin right here at this corner, so that's 0, 0. We know that the center of gravity has to be using the symmetry principle. Center of gravity always lies on an axis of symmetry. So we could split this way. It's got to be on that line. It's also got to be on this line. It's also got to be on this diagonal line and this diagonal line. Center of gravity's got to be right there for a square. Right here for this square. That coordinate's 1/2, 1.5. So 3 halves, 3 halves. This coordinate is 4, 1. It's 4 because we went over 3 and then over 1 more. So now calculate x bar and y bar for me of this system. We've got 2 plates, or those 2 areas. Those are the coordinates of each of those centroids. So what is x bar and what is y bar? Okay. So I wrote down x bar as the average of the x coordinates and y bar as the average of the y coordinates. If you did this, that's incorrect. Okay? You should have seen how many heads popped up when I said that was incorrect. What? This is not that would be the midpoint of this point and this point. So if I drew the line there, found the midpoint, okay, so it would be somewhere right in there. That'll give me the midpoint, but that's not the center of mass of that system, okay? If we cut out two pieces of cardboard, glued them together in that shape, and tried to find out where they balanced, it wouldn't balance at that point. Why not? Okay, so he said that the point on the left is associated with more mass, and so it should pull the center of gravity that way, and it does. So if we can't just take the average like this, you could do this if the same mass was the same for both of those, but it's not. So what do? We have to weight. Remember the not weight, W-E-I-G-H-T, that weight, not W-A-I-T. Okay, we have to weight the coordinate with the mass. So for x bar, I take the mass or the area of the first one, so the area times the coordinate plus the area times the coordinate of the other one, which is 1, which is 4. So I'm working just with the x's right now. And then I have to divide by the total area, or the total weight, which is 13. I've got 9 on the one side, 4 on the other side. And then for y bar, it'll be 9 times 3 halves plus 4 times 1 all over 13. So it is an average, but it's a weighted average. So each of those points isn't associated with the same amount. You've got to weight by the amount. Okay. And now we can go back and answer the question, the first question that came up. So so one way to think about the coordinate of this system here, this x coordinate, is the centroid of this is calculating the centroid of this area, of this region, and calculating the centroid of this entire region. And then you've got to subtract, do some math with the same math we just did, except you're going to be subtracting the one from the other one. And so for this big thing here, you could find the centroid, and that is, let me draw it again down here. So this is square root of x, 1/2 the 1/2 the square root of x squared from 0 to 1 dx all over that area. So that's going to be the integral from the square root of x dx from 0 to 1. That's going to be the y bar of that part. So right there. But what we need to do is also do something about this part, because we don't want this part. So we have to subtract with a weighted average, but it's going to be a weighted difference, with x squared 1/2 0 to 1 over x squared dx from 0 to 1. And so then we have, this will give me the y bar of one of those, and this will give me the y bar of the second one. And then I can weight them. I can multiply each one by their respective weights and add the y bars together and then divide, add those moments together. And if you do that, you can see that we've got this this square root x squared and this x squared squared, and that still comes out when you do that, when you do the math to get that thing. Does that help to answer your question? Who answered that? So, whatever that was. Sorry, I don't want to take time to go through that whole derivation, but it comes from thinking about this as two separate things. So you can also think about it as in a slice. You're calculating to find the center of gravity of this piece. You actually find the center of gravity of this tall rectangle, and then the center of gravity of this one, and then you do a weighted difference instead of a weighted average. So, yep. Yeah, we only did the y bar here. What's the easy? Is that what your question was? Yeah. Yeah. Right. We're going to chop it up this way to think about y or x. So, okay. What's the easy way to get x bar in this example here without doing calculus? It's the same as y bar because it's symmetric. Because it's symmetric along the line y equals x. So the x coordinate has to be the same as the y coordinate. So using symmetry, we don't have to do the calculus. Okay. So why are the formulas different? So we're good at figuring out where the center of gravity is of a rectangle, right? You go halfway, you just split the difference in each direction, and you can figure out where the center of gravity is. Did you have a question? Okay. All right. So we're going to do what we always do when we get complex problems in this class. We chop it up into small pieces that aren't so complex, and then we'll put them together. So we can chop this up, and each of the pieces look an awfully lot like a rectangle. Okay. And if we're thinking about where the x-coordinates are, well, the x-coordinate of each of these pieces is... The x-coordinate of each of those pieces is about the midpoint, right? So, but the midpoint is pretty close to, and the midpoint is, if you have the midpoint, it's just going to be the x-coordinate there. So if you pick xi to be the midpoint, then it's going to be xi times the area. So we need a coordinate times an area, or a coordinate times a weight. What's the weight associated with this rectangle? What's the area associated with that rectangle? What's the width of the rectangle? What's the height of the rectangle? F of x. So here you have f of xi. So here you have approximately the x-coordinate that you're at of the slice times the area. And then we have to add those up. You do have to divide by the total area, but the total area is, we already know how to do that with an integral. Okay. So here, this is just doing what we just did with those two rectangles. We found the x-coordinate of each, we multiplied by the weight or the area associated with each of the rectangles, and we added them up, and then you divide by the total area. So that's just what we've done so far. And if you want to get more precise or get better estimates, you take the limit as n goes to infinity, and this piece is just the definition of an integral. So that's the integral of x, f of x, dx from a to b, over the integral from a to b, f of x, dx, which is just the area. So that's the x bar. Well, what about y bar? Well, if we take this one of these arbitrary rectangles,
the y-coordinate is going to be halfway up. Well, what's the distance all the way up? F of x. The height is f of x. So halfway up is going to be 1/2 f of x. So we have 1/2 f of xi, but we have to multiply that. That's our coordinate. We have to multiply that by what? The area, which is the same thing we did here, multiply by the area here and the coordinate, and then add those all up together. And go to divide by the area. And when you take the limit, then what happens? You can see where the 1/2 comes from now. Would that help? You can see where the 1/2 comes from because the y-coordinate, if you chop it up with respect to x, the y-coordinate is 1/2 your f of x. And so you get this f of x times the f of x. One of these is from the area, and the other one is the height of your coordinate, 1/2 the height of the coordinate. So you get the f of x squared over 2 dx, a to b divided by the area. That's y bar. Okay, so questions about derivation, where these formulas come from? Oh, so if you're integrating with respect to y, then the thinking reverses, and if you're doing dy, then y bar is going to be, I should let you guys talk about this. If you're integrating with respect to y and you want y bar, what would the formula be in there? So talk to your neighbor.
Exactly.
Okay. So if you're chopping up with respect to y, then the thinking is much closer with what we did when we chopped it up with respect to x. So if this is our region here, then you're just thinking about the y coordinates of each of these rectangles, and the y coordinates is about your height, which is y. It's about your input. And so here we're going to have to do it in two cases, so that's not a great example, but you got me on this one. So if it's like this and you're integrating with respect to y, in this case, then up here would just be y g of y, like the function one, like f of x with respect to x, because your y is your coordinate and g of y dy will be your area. So here, in this exact same thing, you've got to break it up a little bit and do something a little bit different. But yeah, I probably confused you more than answered your question there. But I don't know if we give you any problems where you have to do that. But if you're thinking about the area from here over, which is what integrating g of y will do, then your y coordinate, like to calculate your y coordinate, you're basically using your x coordinate formula up here. So, and then vice versa, it would be to figure out your x bar in this case, it would be g of y squared divided by 2 dy. So you reverse those. Okay, that was not a good explanation. I haven't thought a lot about that, as you can tell. Okay, other questions that I can poorly answer? Maybe the weekend wasn't long enough. I'll blame it on my migraine yesterday. So. Okay, let's do some. Okay, here's a right triangle. This is the base, and this is the height. So this is the line. So this is the origin right there. So this is the line. Y equals h over bx. So calculate the x coordinate and the y coordinate of the centroid of the right triangle. Okay? So that's your job. Calculate the x coordinate and the y coordinate of that triangle. Those of you in statics know this already off the top of your head, I imagine. Right? Yeah. Well, depending on how you're. Yeah. You're doing it of this entire triangle. So oh, sorry, you're talking about big A or little a? The area, or you're talking about your lower coordinate? Yeah. Yeah, so it's 0. I said this was the origin. I should have put it on there. So, no, that was poor teaching. So. Okay, so my work's up here. So I calculated x bar. We won't have time probably to do y bar. But if you're clever about it, you actually don't have to do the calculus to figure out y bar. So So I multiplied my x times the function value, so h over bx, and I divided by the area. Okay, so you don't have to do the calculus to find the area of the right triangle, although I had some do that last period. So and then the antiderivative here, because you get h over bx squared, you're trying to find the antiderivative of, so you're going to get an x cubed over 3. That's right here, multiplied by your hb, which is right there, and that's my coefficient that I brought out front. And I'm going from x equals 0 to x equals b, and so everywhere there's an x, I'm evaluating with b. When I plug in 0, all the terms go to 0. So I end up with hb cubed over b times 3, and I'm multiplying that by 2 over bh, and this over b here and this divided by b here makes it so that b cubed just becomes a b to the first, and the h's divide out, so I end up with 2/3 b. So that means the center of gravity is, if I divided this distance up into 3 parts, it would balance on this line right here. Okay, and now if we're clever, we realize that we've actually already done the height also, because it's just another right triangle. If we just think about this as the base and this is the height, then we know it would be, if we split this up into three congruent pieces, that it would be right here. So 2/3 down from the vertex, or 1/3 up from here. And that works for any triangle. Doesn't have to be a right triangle. If you drop a perpendicular from a vertex, then you measure up 1/3, then the center of gravity has to lie on that line. If we take a perpendicular here down to that line, split it up into 3 pieces, oops, that's not thirds, then it has to lie on this line here. So the center of gravity will be right there. That's supposed to be a 1/3. Okay. If you're just dealing with triangles, the easiest way to find the centroid is to connect medians. So where this is the same, those lengths are the same, these lengths are the same, and the centroid will be right there. And this length here is 1/3 of this entire length. So, and this piece here is 2/3 the entire length. Okay, in the last 5 minutes, let me show you why these are so cool. Okay, you guys remember this problem where you were calculating the volume of a torus? So we had, this is big R here, and this is little r here, radius, and we were spinning that around. Right, we used the disks and the shell method. Okay, well, if you know where the centroid is, then you can use what's called the Theorem of Pappus. Okay, so the Theorem of Pappus says to calculate the volume, you take the area times the distance the centroid travels. Well, the centroid is right here, right in the middle of that circle. The area of that circle is pi r squared with the little r. And how far does that centroid travel as it moves around? 2 pi times big R. Okay, it took us 30 seconds. So some of you took an hour on that problem. So that's for volume of revolutions. Well, what about work problems? you can simplify work problems if you know where the centroid is to multiplying the distance the centroid travels times the weight. So remember we had that hanging flag problem where we had a 100-foot flag that weighed 2,000 pounds. It was the big Y flag hanging off of the Tanner building. Well, where's the centroid of this flag? Right there in the middle. So how far does the centroid travel if we lift the flag all the way to the top? 50 feet. So 50 feet times 2,000 pounds. There, done. Okay. What about the pump problems? If you know, the pump one's sometimes harder because you don't always know where the centroid is with some of these shapes. But if you do, like here's a shape where this is 4 and maybe the radius is 3 and we're pumping up another 2 feet right here. And we're pumping all the water out of this tank. Well, because of symmetry, I know where the centroid is. And its centroid is going to be halfway up. So the depth here of the centroid will be 2. So we need to multiply, we need to find the weight, which if this is water would be 62.5 times, times the volume. And the volume will be 3 squared pi. That's the area of the top, times the height, which is 4. So this much will be a weight. And how far does the distance to the centroid travel if I pump it all the way up? 4 feet. So that's nice if you know the centroid, if you know where the centroid is. If you've got a hemisphere like this, you're toast. We're teaching you how to find centroids of 2-dimensional objects. This is a 3-dimensional object. This is a different beast. And so if you don't know this, then you've either got to set up a double integral to find the centroid, which you don't know how to do yet, or just calculate you just have to set up the integral anyway to find work. So hydrostatic force in the last minute. How do you find the hydrostatic force? Well, that's the area of your region times the depth of the centroid times the density of water, or whatever your liquid is, times the density. So if this is water, that's 62.5. There's the density. Area, 3 times 4 over 2. Depth of the centroid. Well, now we just figured out the depth of the centroid of, we know where the centroids are for triangles. No wonder my voice is hurting. So the depth of the centroid, I'm going to have to come down 1/3 of this distance. So I need to come down 4/3 here. This distance will be 4/3, but then I have to add on another 2, so 2 plus 4/3. And there you go. That will be the hydrostatic force. And the reason it is the hydrostatic force is because if you take this region and you turn it sideways, if you put it at the very top of the region, that's not going to be enough weight of water over it to be the same as the hydrostatic force. If you put it at the very bottom of the region, it'll be too much water over it for it to be the hydrostatic force. If you twist it and put it right at where the centroid is, you get exactly the right amount of water over it. So the weight of that water is the hydrostatic force on the region. Have a great day.
I have a question about like 2 or 1 of the
Well, I know how to make
examples
good
before
microwave
this one.
fudge.